Hi everybody, thank you for joining me with revision for Physics Paper 1, which is tomorrow afternoon. Hopefully you've done lots of revision. If you haven't, then hopefully this will help. I think it helps if you have a pen and paper, but I know that some people are taking snapshots with their phone, and try and remember that you can actually watch this afterwards if you click on, I think it's My Story, and then you can watch it again and then you can press pause. Okay, so as before, I'll wait a couple of minutes for all the people that want to join in, and then I'll be going through what's on the list. So series and parallel circuits, radioactive decay, energy change, and then the required practicals. I think we all know that I'm not going to be able to go through everything. Hopefully some of what I do will come up in your exam, and hopefully it will help you. Hope your exams have gone okay so far. I know that it was the maths and geography exam today, and I hope they went well for you. I know that we've got obviously lots of students from my school watching, but I also know that the students from Kingsmead that watch, and I believe that we're joined by students from Robert Blake today. So hopefully you'll all find it very useful. I think you've been recommended by Miss Dyer to watch this session. Okay, so we'll start in just 1 minute. Welcome to those schools and whoever else is watching, and I'll be trying to help you with series and parallel circuits, radioactive decay, energy change, and then the required practical. Okay, and I'll try and make it as easy as I can to follow, so that you all understand it as best as you can. But don't worry if you don't. You can always watch it again afterwards, or you can come and see me tomorrow morning. I'll be in my room from 7 o'clock, so you're welcome to pop along and ask me for any help that you need then. Or if you've got anything that you'd like to know after this session, then by all means just pop me an email and I'll try and go through that with you then. Okay, so to start with, series and parallel circuits. Okay, so concentrating. So if we start with a series circuit. And I'm just going to draw a series circuit for you. So we've got a cell, and cells joined together to make batteries. And a series circuit, so remember these lines are wires, and travelling through the wire is electricity as current. And we might have a light bulb there, and we might have a light bulb there. Okay, so that's a simple series circuit, and it just means the current has only got one way to go. Now when we connect, well, we can measure, there's different things. You've got to know for a series circuit about current, you've got to know about potential difference, and which is the same for your exam as voltage, they accept either, and also resistance. Okay, so those three words you need to be familiar with when you see the circuits that you're going to get given in the exam, and I imagine you will get given a circuit. Now when you measure the current is with an ammeter, and that's measured in amps. The potential difference is measured with a voltmeter, and that is voltage. Okay, so you might well know this, so just to recap for some of you. And resistance is measured in something called ohms. Okay, now if you measure the current with an ammeter, the ammeters are fixed in exactly the same line as the wire. So that's A, so I'm going to call that A1, and that's A2. 2. Okay, so the current is the flow of the electrical charge going round a circuit, and it's measured in amps. Now if that current there is 5 amps, so there's 5 amps of electrical current going around there. Because they've only got one way to go, there's got to be 5 amps there. Okay, so the current is the same everywhere in a series circuit. I think when I was at school, the teacher says, don't think of amps, just think of cars. So if you've got 5 cars going down that road, because they've only got one way to go, there'll be 5 cars going down that road as well, because there's nowhere else for them to go. Now that's current, okay? Now, to make it a bit easier, I'm going to draw it again, but try and show you about voltage. Okay, so we don't need the ammeters now. Whoa. Okay, so same again, but this time we're going to look at voltage. Now current, the ammeter was just in line with the wire. So sometimes they say that ammeters are connected in series, which just means in line. A voltmeter has to be connected differently. So a voltmeter, imagine it's got arms, and the voltmeter has one arm one side of the bulb and one side the other side, because a voltmeter measures the potential difference, and it wants to measure the difference between the two ends. So a voltmeter has to be connected like that. And then if you have a voltmeter for the battery, again it's V, again one side goes there and one goes there. Oops, can you see that? Okay, so a voltmeter isn't connected in the same way as an ammeter. Now, if we look at the voltage then for a series circuit, if we say that the voltage across the battery is 5 volts, then the voltage across each light bulb will be 2.5 volts and 2.5 volts. Okay? So for a series circuit, there is the same current going through each component, and the total potential difference, or the total voltage there, is shared between the different components. So if there was 3 light bulbs there, you'd have to divide whatever the battery is by 3. If there was 4 light bulbs, you divide it by 4, and so on. So the current is exactly the same in a series circuit. In a series circuit, the voltage is shared. So if the battery is 5 volts, then you have to divide it by 2 if you've got 2 components in the circuit. Okay, so that is for a series circuit. Right, if we try and draw now a parallel circuit. Okay, so P-A-R-A-L-L-E-L, so a parallel circuit. So again, we've got a battery, and a parallel circuit is a little bit different. We'll just do the one that goes up there. And we'll say that goes there. Okay, so this time the current that goes round has got a choice of different ways to go. So if you've got an ammeter there, remember the ammeter has to be connected in line with the wire. If we say that is 5 amps, then the current, remember, which is 5 amps, is the flow of the charge. So there's 5 amps going this way. Now it's got a choice. You can either go that way or it can go that way. And it tends to go the way of least resistance, or the easiest way. Because they're exactly the same, 5 amps goes there, you'd get 2.5 amps there, and you'd get 2.5 amps there. Okay, so when you've got a parallel circuit, then you get that. So 4 component series in parallel, the potential difference across each component is the same. The total from it is the sum of that. Okay, so that's that. Now if we've got the voltage, so there's the voltmeter, and again remember we connect the voltmeter like that, and we'll do another voltmeter there, and we'll do another voltmeter there. Okay, so we've got 3 voltmeters, and let's say that that is 5 volts. Then the voltage is exactly the same. So that would be 5 volts, and that would be 5 volts. So for components connected in parallel, the potential difference across each component is exactly the same. So 5 volts, 5 volts, 5 volts. The total current through the whole circuit is the sum of the current through the separate components, and so on. Okay, so that's a brief summary of series and parallel circuits. It's important to remember your symbols. So this could be a snapshot, or perhaps watch it again later. Okay, so these are the symbols that you need to know for your exam. I imagine if you do the foundation paper, then they're bound to ask you at least one of these. Okay, so I'd be clear on all of them. They're all equally as important. So if you're struggling with your revision and you're doing the foundation paper, then this could be a good starting point, making sure that you learn those ready for tomorrow. Remember, a cell is just one of those, and several cells connected together you call a battery. Okay, right, so looking at what we've done so far, just moving that up. We've looked at series and parallel circuits, tried to look at the current and the voltage, and we've looked briefly at symbols. Right, I'm going to talk about radioactive decay now, which is a little bit different. And I think it's quite straightforward. So I think that this is something we can all do, and hopefully again will help you in your exam tomorrow. So radioactive decay. You probably all know there's 3 types. There's alpha. Now an alpha particle is 2 protons, it's 2 electrons, and it's sometimes written as 4/2 He. Okay, so an alpha particle is 2 protons and 2 electrons, and it's sometimes written as 4/2 He. So it's helium. It's actually a helium nucleus because the helium has got a proton number of 2. It's got a difference of 2, which is the neutrons. Actually, just correct myself, an alpha particle is 2 protons and it's 2 neutrons because it's a 2 plus ion and it's lost its 2 electrons. So better get that right. I do apologise. Now, if you've got an element like 22890 thorium, okay, you don't need to learn these. You will be given something and you just need to work them out. It might say, right, you've got an atom of thorium, and it'd give you that in the exam. You've got to work out what you get if it decays by alpha decay. Now remember that an alpha particle is just 4/2 He. That's the bit that you have to remember. So what you do is you take 4 off 228, so that gives you 224, and you take 2 off 90, which would give you 88. And this element that has the atomic number of 88 is Ra, which is radium. Now to check that we've done it right, the top number on this side, 224 plus 4, has to equal the top number on the other side, which is 228. The bottom number, 88 plus 2, equals 90. So that is an equation where thorium has lost an alpha particle. That is an alpha particle. That's the bit you've got to remember. Okay? So it might just give you that and say what happens. So the first thing you do is you remember that that's an alpha particle, and you just make sure the top numbers and the bottom numbers add up together. Okay, so that is an alpha decay. So let's just underline that. You can also have beta. Now a beta particle is actually an electron. Okay, so we said that an alpha particle was 2 protons and 2 neutrons, which is that. A beta particle is just an electron. Now if we draw an equation for that, then again the examiner would give you something like this. So that's potassium. The bottom number's 19 and that makes it potassium. You might remember that the top number for potassium could be 38, it could be 39, it could be 40, it could be 41. The top number can be different because you can have isotopes of elements. So if you've got an isotope, it tends to be quite unstable, and that's why it decays like we're showing. So that would decay. Now a beta particle, you need to remember, is 0, -1, and we show it like that. So key things to remember. An alpha particle is 4/2 He. That is an alpha particle. A beta particle is 0, -1. Okay, you don't have to worry about the 2 plus. So an alpha particle is that, a beta particle is that. Now again, the top number, so we're going to lose now by beta decay. So we've got a beta particle. Now the top number has to be the same as the bottom number. So 40 and 0 is 40. But this time we've got 19. So this number is a bit confusing. That has to be 20 because 20 -1 would give you 19. So it's probably easier if you don't write it like that. I think I would write 40 19K, and then what you get is 40 20 Ca plus 0/-1b, and then you can check it because 40 plus 0 is 40 and 20 -1 is 19. Okay, now you might, if you've been doing your revision, think, well hang on a minute, why is a beta particle, if you've said it's an electron, why is the atomic number changing by 1? And that's because inside the nucleus, the neutron breaks up into an electron and a proton. The proton stays in the nucleus and the electron leaves the nucleus. Okay, so an alpha particle is that. Please note, I'm emphasizing that. That is an alpha particle. So if an element decays by alpha radiation, it loses that. If an element decays by beta radiation, then it loses that. And the top numbers and the bottom numbers have to add up to the same. The third one that you can have is gamma. And gamma, so these are particles. That's a particle. It's quite a big particle. Beta is a particle. It's a very small particle. And gamma isn't a particle at all. It's electromagnetic radiation. And I'm sure you've heard the song in science quite a few times. Radio waves, microwaves, infrared radiation, and gamma rays is one of those. Okay, now if you have gamma radiation, it does not change the nucleus. Okay, so you don't need to remember a nuclear equation for gamma. Okay, but for alpha, that's an alpha particle. For beta, that's a beta particle. and these are called nuclear equations. Okay, so you really need to make sure that you know those. Right, if I go back to what I'm trying to go through. So we've got series and parallel circuits, cut symbols, radioactive decay. Right, then I thought I'd have a bash at helping you with energy change. Okay, so we'll just have a 1 minute, 2 minute break. Okay, and then we're going to go through specific heat capacity. Okay, so just a minute and then we'll go through that in a second. Okay then, I know that's not 2 minutes, but we'll start now. So the definition of specific heat capacity, and this is a required practical, okay, so it's really important to get this. It is, and I would learn this definition off by heart. It's the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree C. Okay, now the examiner wants you to write the amount of energy to raise the temperature of 1 kilogram of the substance by 1 degree. Okay, that's really important. Now if you think of a beaker that's got a little bit of water, and then you think of a really big swimming pool that's got a lot of water. So definition, the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree C. Now clearly it takes more energy to raise the temperature of something if it's got a much bigger mass or volume. Now a question, okay, so this could be a required practical. So you've got to work out now the specific heat capacity of, and it could be anything. They will say what's the specific heat capacity of something. So I'm going to make something up and we're going to say vegetable oil. Okay, but remember it could be absolutely anything that they ask you. Now you want to remember a setup of equipment. So you need to start off with, sorry that's not very good drawing, a balance. Okay, so let's say it's on 0.00 to start with. So you've got a balance and you've got your vegetable oil inside it. Okay, so there's the vegetable oil and you've got a balance. Now you need to have a, let's try and use a different pen, a thermometer. Okay, so you need to have a thermometer, and you also need to have something else which is called an immersion heater. Okay, so that's basically a heater that heats it up, and that's the thermometer and that measures the temperature. So in the exam, remember, thermometer, immersion heater. Now the immersion heater has to be connected to something that's called a Joulemeter. And if you see the word joule, try and think of energy. So that must be measuring the energy. And that is then connected to a battery or a power pack. Okay, so you've got your vegetable oil, and if you're asked to work out the specific heat capacity of the vegetable oil or whatever it is, you need to have a thermometer, an immersion heater, and then you need to have the Joulemeter attached to a battery. Okay, first thing you do is you set the balance, same as the weighing scales, but we say balance in science, to 0. There's no point going up to the balance and it reads 25.6 because you'll have no idea how heavy the thing is that you're doing. So set balance to 0. Number 2, you record the mass of your vegetable oil or the mass of whatever it is. So you have to have the mass, and I'm going to say that the mass of that vegetable oil is 0.95 kilograms. Okay, so you've got to weigh it. So I've got 0.95 kilograms. Right, number 3, you record the starting temperature on a hot day. That will be different to a cold day. So let's say it starts off at 20 degrees C. 20 degrees C. Okay, so that's that. Number 4, you've got to wrap the beaker in insulation. Okay, if you're measuring the temperature of something, you don't want all the heat coming out the sides. So you have to put insulation around it and make sure it's all wrapped up like a flask. So there's all the insulation. Remember, we're trying to work out the heat capacity of this oil. Okay, so you do those 4 things first. Number 5, you leave for about 30 minutes to allow the temperature to rise, because obviously you're heating it and you're trying to measure what's going on there. And almost finished. Number 6, you read the Joulemeter, and let's just say that the Joulemeter says a big number like 87258 joules. Okay, so the numbers highlighted are what we need. So we know that we started off with 0.95 kilogram because we weighed it. We know that the temperature at the start was 20, and we know that when we've done the experiment, this Joulemeter gives us that energy reading. And then lastly, you record the final temperature. And let's say the final temperature is 75 degrees C. Okay, now they are the 3 things that you need to know to work out specific heat capacity. You need to know the mass of the vegetable oil, you need to know the temperature at the start, the temperature at the end, and you need to know what the Joulemeter showed you. Now you then have to use an equation which is delta E equals times C times that. So a triangle means a change. And that looks complicated, okay? But it's not. M is the mass. Now the mass has to be in kilograms. And luckily, our mass is in kilograms. It's 0.95. The C is the specific heat capacity. Okay, that is what we're trying to work out. And that is a weird way, but that means the change in the temperature. Now the temperature started at 20 and it went up to 75. So I'll just write change in temperature. And delta E is the energy that the Joulemeter gives you, which is that. So that is change in energy. Okay, now that's fine, but we're trying to work out C, because C is the specific heat capacity. Okay, and that's difficult to work out, so we need to rearrange that equation for C. So I wouldn't be working out this in the exam. I would learn now that C is delta E, which is the change in the energy, divided by M, which is the mass, times the change in the temperature. Okay, so that is what I'd learn. You'll get given that, but make sure you can rearrange it. Delta E is the change in the energy. So that is 87258 joules. You divide that by the mass which you've got, which is 0.95, and you times that by the change in the temperature. The temperature started at 20, it went up to 75, so the difference between those two numbers is 55. Okay, so the question was work out the specific heat capacity. I've told you that I suggest you learn that definition. Okay, so the definition is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree. I wouldn't worry about what I was saying there. Okay, that's the definition. The specific heat capacity of vegetable oil, that's the question that we've got here, but it could be anything. It could be vegetable oil, they could give you a metal, and then we'd have to put holes in the metal to put the heater in and to put the thermometer in. They could give you anything. But whatever it is, you need to put a thermometer into it, because we've got to know the change in the temperature. You've got to measure the mass of it, so we need to put it onto a balance, and we need to have a Joulemeter. So try and remember, so we need a thermometer, so that's 1, because we've got to heat it up. We need a heater, that's 2, and we need a Joulemeter, that's 3, and a balance, that's 4. Okay, because we need to know these things. We need to know the mass of it, so therefore we have to weigh it. We need to know the amount of energy, so we need to have a Joulemeter, and we need to know the change in the temperature. Okay, so I've spent a bit of time on that. I think that's really important for you to learn. Okay, if we go back now to what we were saying at the start. So series and parallel circuits, make sure you know about current and voltage in series circuits, current and voltage in parallel circuits. Make sure you can work them out, and make sure you know the different symbols. We've talked about radioactive decay. You can have alpha, you can have beta, you can have gamma, and then we've looked at energy change, and we've focused on that required practical that we've done now. Okay? So if I just say a quick recap perhaps. So in a series circuit, there's only one way to go. The current is exactly the same anywhere in a series circuit. In the voltage in a series circuit, the voltage of the battery, so the total voltage of that battery, gets split depending on how many components there are. So if there's 2 components, you divide the battery voltage by 2. If there are 3 components, you divide the battery voltage by 3. Okay? For a parallel circuit, then the current splits along the different pathways that it can follow. So if you've got 5 amps there, you could have 2.5 amps there, and you could have 2.5 amps there. The voltage, if you've got 5 volts there, then that gives you 5 volts there and 5 volts there. So the potential difference, the voltage, is the same if there's one component in a parallel circuit. Then we looked at radioactive decay, and we said that there's 3 types of particle. So there's alpha, there's beta, and there's gamma. And the alpha particle is that. So if you've got something and it will give you this, so this is thorium, but it will just give you, it will make something up. And it will say what happens when that loses one of those. So what you've got to do is you've got to take 4 off the top number and you've got to take 2 off the bottom number. And that's what you get. And you check it by adding the top numbers on each side and the bottom numbers on each side, and that should equal the same as what's over there. If you have beta decay, so beta particle is an electron. So if you've got potassium, for example, or we don't need to know what element it is really, if we've got 4019 there and it loses a beta particle, then you've got to make sure the bottom number is 1 more than that. Okay, that's all you have to remember. So for alpha particle, that is 4 less and that is 2 less. For a beta particle, the bottom number is 1 more. Okay, and again, make sure that 40 plus 0 equals 40 and 20 minus 1 equals 19. The reason that happens is because in the nucleus, the neutron breaks up into, or perhaps breaks up isn't the best phrase, a neutron changes into an electron and a proton. The proton stays in the nucleus. That's why the number's gone up to 20, because it's got an extra proton, and the electron has been lost. Gamma radiation is part of the electromagnetic spectrum, and that doesn't change the nucleus at all. Okay, so you don't need to know nuclear equations for that. Then mention specific heat capacity, and the definition is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degrees. So different substances would have a different specific heat capacity. In the exam, you might get asked to how would you do an experiment for that? And the experiment, you need to know this equation, okay? And the mass you need, the change in the temperature you need, and you need to know the energy that's in joules. So you measure the mass of it, which in this case was 0.95 kilograms. You measure the starting temperature, which in this case was 20 degrees C. You cover it in insulation. Lots of students always forget that. So you cover it in insulation, you heat it up for about 30 minutes, and you measure how much energy that requires. So I've made up a number there. That's with a Joulemeter, and then you record the final temperature, which I've got there. Okay, so the numbers highlighted are what you need. If you need specific heat capacity, you need to rearrange the equation. So I just learned that, okay? I wouldn't be rearranging it in the exam. So spend a couple of minutes to learn that now. C is the specific heat capacity. E is the energy. So the energy goes at the top, the mass goes at the bottom, and the change in the temperature goes at the bottom too. So because it started at 20 and ended at 75, then the change in the temperature was 55. Okay, then if we look at another required practical, which is resistance of a wire. Okay, so resistance makes it harder for the current to flow. I've just been teaching my class this morning, and if you've got a short wire and if you've got a long wire, then you've got current trying to get into it. That has a greater resistance because it's a longer wire, and that has a shorter wire has less resistance. Okay, so that's a long wire and that's a short wire. Okay, so the current's trying to flow through it, and the current finds it more difficult to get through a longer wire because it's got lots of metal ions all in it. So the current is difficult to flow through, so the current slows down, so you have a lower current. But if it's a short wire, there aren't as many metal ions in there, so the current can go through a little bit faster. Okay, so bigger resistance for a long wire, smaller resistance for a shorter wire. Now to investigate that, you need a battery. So let's draw the battery properly. And you need to have a piece of wire. Okay, so the wire will just represent like that. So there's my piece of wire, and that will be clamped there. We need to measure the current, and that then goes back to the battery. Okay, now there's my wire. We've got the ammeter that measures the current, and we've got perhaps a voltmeter that measures the voltage. Remember how the ammeter is just connected in series, so just in line with the rest of it, whereas the voltmeter is different. That's connected in parallel, and I always imagine the voltmeter as having two arms. One arm grabs either side of what it's measuring the difference of. Okay, now important, voltage equals current times the resistance. Okay, so voltage is current times resistance. Voltage is in volts, current is amps, and resistance is in what's called ohms. Okay, so the way you'd want to do that is you've got your wire. So there's your wire, and we want to put the wire onto a meter ruler because we're going to try and investigate how the length of the wire affects the resistance. So you'd have crocodile clips there, and then that would go to the rest of your circuit. Okay, now you could measure the voltage for 10 centimeters, the voltage for 20 centimeters, the voltage for 30 centimeters, and you know the current there. And then you can use voltage equals current times resistance, or you could measure the current at 10 centimeters, at 20, at 30, and then use the voltage of the battery. But to calculate resistance, you need to use that equation, and that equation is called Ohm's law, and that's very, very important. If you sometimes get asked to draw a graph, so if you've got length of wire and you've got along the side resistance, then as the length of wire increases, so does the resistance. It's very difficult to get the crocodile clips to exactly zero, so sometimes you get a point just above there, and that's called a zero error because it should go through zero, but sometimes it doesn't just because of the difficulty in setting up the equipment. If the temperature of the wire increases, which it does when the current going through it is greater, then that increases the resistance as well. So it's important to use a low voltage or potential difference, same thing. Use a low potential difference and turn off the current between readings. Turn off the current between readings. Can't put it on. But they are the two things that are important. So you use a low voltage or use a low potential difference, and you turn off the current between readings because you don't want the temperature of the wire to go too high, because that would make the resistance increase and mess up your results. So I have tried to go through series and parallel circuits, so make sure you can explain the current and the voltage and the resistance in series and parallel circuits. Radioactive decay, alpha, beta and gamma, and energy change. Try and remember that for a series circuit, the resistance, you just add up the resistance of each component, and that gives you the total resistance. And we've gone through the recorded practical for the resistance of a wire and the interchange. Okay, so I'll be in tomorrow from 7 AM in A6. I really hope that that has helped you just a little bit with your revision. It's quite late now, so I wouldn't do much more. Going to the exam feeling really confident. Okay, I know that all the people that I've taught have done an amazing job with their revision, and if you've been sat there listening to this, then well done to you. Okay, you're obviously doing your best, and that is all you can do. Remember, the video will be available all night and tomorrow, somewhere on my profile. I'll be in tomorrow morning. If you've got any questions now that you'd like to ask, then pop me an email. Otherwise, thank you very much for listening, and have a nice night, and good luck with your exams. Okay, bye.